All right, everybody, back for round two of the Autopilot lecture by popular demand. This one will go a little bit faster, and I also will show you the mission planner software as well as a little bit of the Autopilot website. So, Autopilot is, it's a pretty complex thing. The theory behind it starts with guidance, moves to navigation and control pretty quickly. Very in-depth. There's a whole lot of material on it, lots of scholarly articles, entire classes that you can take on a university and graduate level to teach you about different types of control and all that. So don't think that you'll become a specialist in it in one semester worth of work. But we'll at least touch on the theory about it. Then move to the hardware, what you'll all be working with in the aircraft, and then the software, the ground control station side, and how to put that all together with integration. The picture at the top here is a kind of a standard block diagram look, and how autopilots generally work, and we'll talk about this a little bit more. It's a method called successive loop closure, where you have a this will be one loop here, and as the time goes on, you've got essentially something that comes through here and loops through here. You also have a loop going here. So these are successive loops, and they are closing the system, hence successive loop closure. So that's more or less how it works on a kind of super low level or super high level. And you won't need to know the super specifics of it, but you will need to know a good amount of how this all works. So the theory of this for how to get it all working, you're controlling a fully nonlinear 6-degree freedom system, the aircraft. It's not nice like a car that drives on the road where you don't have to control altitude and your turning is kind of limited to one dimension. You get all 6 degrees to deal with. So you identify this behavior with a process called parameter identification. You won't really have to do that a whole lot in this, but in the real world, that's a very real thing that happens. So you provide a controller for each dynamic mode. So you've got Dutch roll, phugoid, short period, spiral mode, all those kinds of things that you need to control to have an aircraft that's stable all the time with no human intervention. You then provide a controller for that. Provide a controller for the guidance and navigation, nav where you are, guidance where you're heading. The ground station does a really good job of putting this all into one package. So perimeter identification, as I said, you won't really have to do that in this, but it's great to have an idea of what's actually going on here. So stability derivatives, how maybe the aircraft's yawing moment is affected by a side slip or a gust from the side. Things like that really define how the aircraft moves are your parameters. So to identify how those happen, it's related to a whole lot of things, really hard to do by hand. Most of the time there's pretty specific and very complicated programs that are used to figure this out. CFD, CAD, and programs like AVL or XFlyer, OpenVSP, they can all do some sort of help with getting you towards parameter identification. You really do need to combine multiple sources to get a real answer for anything. And those are predicted values. If you move into the real world where you have an aircraft, you can measure values, be a flight test or a wind tunnel, to help you glean some of those numbers. So controllers are a way that you control how this aircraft is going to actually work. Once again, if you're going to try to control Dutch roll, which the GIF down there in the bottom right is demonstrating, or phugoid, which is kind of a slow pitching that's elevator coupled with angle of attack. So you use a linearized equation of motion, and once again, a successive loop closure to create a controller for each of those. So you're defining these system inputs and outputs, can be single input, single output, multiple input, multiple output. Once again, controls classes on aircraft dynamics and that we'll get into a lot more than we'll ever get into here. Generally, PID controls used in those controllers to get them to work, and you can do filtering, saturation, all sorts of stuff to really get the the behavior that you want out of the system. So navigation is where you're at. The most common way currently to do that is with a GNSS, or GPS GLONASS, as you see there. There's a system called RTK that's real-time kinematics. That is essentially getting you a better answer for your GPS. So it may reduce a GPS latitude longitude error from 3 meters down to a couple of centimeters. Vertically, it may make 5 meters down to a 1 meter error. So you're essentially just giving it better position data. I don't think any of the teams are using real-time kinematics for any of this. It's fairly expensive. Probably not a whole lot of payoff for the project as it is here. You also have inertial systems, so INS, based on accelerometers, gyros, and that kind of thing. Nice example, Minuteman ballistic missile uses an inertial system, does not use GPS or anything, so that it itself knows its location at any point in its flight path. A lot of older aircraft use inertial systems as well, before GPS existed, and maybe when you were out of range of ground-based navigational aids. Magnetic compass, which way is north, that gives you really just one direction or 1 degree of freedom answered, but very useful in the total solution. Barometer is a great way to get altitude, a lot more accurate than a GPS vertical solution. Then there's sensor fusion, which ties this all together. The most common way with Kalman filtering, and it's not easy to do. You can sit and drive a Kalman filter, but there's one already built into the ground station's software and firmware, so you won't have to. Guidance is where you're going. So if you draw a line from point A to point B, and you are somewhere in between those points, how do you know how far or how wrong you are? Well, use something called cross-track error. How far to the left or the right you are of that line. Your controller is set so that you say how fast you want to get to that line. But that's limited by a lot of real-world things, including bank angles, airspeed, gravity. It's another big one. So, and then you have the tolerance built in. How close is close enough? Do you need to sit and chase that line within a millimeter? Probably not, but probably better than a kilometer. So as a hardware warning, last year Dr. Mako took a student to the hospital with a cut hand. Not really from any testing issue, kind of a weird freak thing, but it still stands. Please be careful. Duct tape only goes so far, so make sure you're safe with all this. Perform all these tests without a prop. Put a prop on when you already go fly, but preferably not before then. So all of these hardware solutions pretty easily integrate all of the guidance, navigation, and control, as well as the hardware side of things. We'll get to integration later. So this hardware side, you have a Pixhawk, which all of the groups know pretty much about now, and I think all of the groups are using a Pixhawk. It's kind of the, you see on the next slide, it's kind of the first generation. Pixhawk 2, which is a little bit newer, has a little bit different hardware layout, different connectors, or a Pixhawk Mini, which is smaller. Some Raspberry Pi projects, nobody in the Boeing group this year is doing a Raspberry Pi based one, so that's fun. And additionally, as we said with the navigation solution, where you're at. So an external GPS gives you that very accurately, very quickly. Nice to have. Pedostatic system, almost required for any kind of airspeed-based flight paths. So once again, the hardware that some teams are using up on the top, the Pixhawk 2 on the bottom there, have an onboard inertial measurement unit. So accelerometers, gyros, barometer, magnetometer, all on board. Lots of extra items, I2C, UART, CAN bus, and an analog to digital converter, along with several others that you can play around with if you feel like it. And then the telemetry and control radio, which talks to your ground control station. Very nice to have, almost required, I think, for all of the groups and the missions that they're carrying out. And pretty sure all the teams already have these, at least some semblance of this up and running, which is excellent to hear. So I'm obviously not going to describe each individual step of the hardware setup here, but we'll go through some common sticking points, or some issues where people end up in some easily fixable spots, but may not realize it at the onset. So you install your Pixhawk hardware as near the main piece, as near the CG as possible. All of these arrows that you see here, try to keep those facing forward. All of the defaults in the software rely on this orientation being maintained. Not that you can't change that, but it's much easier to stick with the defaults. Only change that if you really need to. And then foam or rubber to dampen vibrations for mounting the main units. Not necessary, or not absolutely necessary, but not a bad idea. So after you've got your Pixhawk installed, you can attach all of your electrical connections. All of your airspeed sensors, your servos, your power module, your GPS, all of that. Make sure everything is attached correctly. Make sure nothing's reversed. I'll get to that in the next slide. Don't pull your wires taut as you have them, installed, and try to avoid a rat's nest. It'll make it a lot easier on everybody if you're not trying to dig through 15 different wires trying to trace one down. So servo wire is a very common issue where people say, "Oh, servo is not working." You just check your servo wires. Chances are you have a connector flip somewhere. So the correct on the left here, these white, yellow, and orange here. So white, yellow, and orange are your signal wires. So they're PWM wires. These red ones in the center are always your positive DC, and the darkest color, so the black here or the brown, is always negative DC. So they should always look like this between the three different standards of wires. They should never look like this. So the easiest way to avoid that is to standardize all your servos, use the same wires throughout. It's not always super practical, but it's a nice idea. It takes some additional planning. Making custom linked servo wires takes a little longer, maybe a tiny bit more expensive. Could you save you some weight and some space? Certainly gives you a nice looking product in the end. So testing, bench testing, creating an iron bird. It's a nice way, almost required way to get everything working together. You can't expect to throw everything in a final aircraft in a suit and just assume that it'll work right off the bat. So you pre-assemble this whole thing as much as possible. Even servo extensions, all of your cameras, your transmitters, GPS, everything. Just slap it on a couple of pieces of foam or wood. It works fairly well. You get a very good idea of how everything works together, mounting orientation, the works. So. And make sure you can get to the Pixhawk. That stands here, as well as in the final aircraft, where hopefully you're not, but you very well may be chasing down wires if you're not careful. So test beds is another good way to get towards a final solution without using your real aircraft. Maybe it's not done. Maybe you don't feel like sacrificing it to the remote control plane gods. So if you use a test bed, you can essentially slap all of your electronics, your cameras on there, and see how they'll work in flight, in association with your ground control station, how to get everything to work. Well, maybe your plane's not ready to fly yet. Your real plane's not ready to fly. You can always use it to test assembly and startup steps. It'd be very good for everybody to get a checklist and or a workflow for how you're going to get your plane ready for each flight. It can get you good on how to use the ground station, the different flight modes, either on the ground station or a RC transmitter, as well as your sensors. Know how your airspeed works, the cameras work, if you happen to use any external sensors, how to get all of that working before you're down to the time limit. You can also use it to create or refine stability models, methods for data collection, making sure that you can pull the data flash logs off of your Pixhawk when you're done. Know how to do that before it actually gets to the point where you want to do that, or you need to do that. Also, you can use a known stable design. Once again, this is mitigating risk of your expensive components. If you've got your expensive camera, your Pixhawk's not cheap, you want to put that in an aircraft that you know is built to be able to fly, and fly it hopefully very well. So on the software, there's a ton of choices. I think by far and large the most useful is Mission Planner. That's what I'll use for the rest of this presentation, and I'll show you that a little bit at the end as well. Also APM Planner, Q Ground Control, and UGCS. there's no absolute right answer, but you need something that'll work. They're all free. But you just need to be able to use what you pick. So start now, take a look. There is a pretty steep learning curve in all of this. Make sure that you can get it working when all's said and done. So that ground control station, the picture over here is maybe a really full-fledged one that most of the groups probably won't get towards, but it's a nice idea, and at least maybe give you some idea of what maybe really would need to happen in the long run. So you use a ground control station for mission planning, right? You set waypoints. You can set a vertical profile, so you tell it to fly at a certain altitude. You can set a point of interest here before or during your mission. If you happen to fly with the camera and you're panning around, you say, oh, there's a spot there that I'd like to look at. You set it as a point of interest, and then you can sit and loiter above a certain location. You're also, once again, if you've got cameras and sensors, that all reports back to Mission Planner. You can even integrate a joystick if you feel like it. If you feel like flying from the ground with a joystick as opposed to an RC transmitter, go for it. Just be cognizant of possible telemetry dropouts if you do that. Once again, on that telemetry, you have real-time info on location, speed, maybe estimated time on target, all of that kind of stuff, as well as diagnostic and status info. Battery level remaining is a very critical one to pay attention to. All sorts of things, especially maybe considering a camera orientation or perhaps vaccine temperature. So these telemetry channels, all of these radios come preset on channel 25 on these radios, on these telemetry radios. I believe everybody should be using a 900 megahertz version. So these are just the steps to change that, and we'll get to that a little bit in the end. More or less, the end goal is to change the net ID here to something that's not the standard 25. And just keep in mind that you have to change the local version. That would be the one that's plugged in via USB, as well as the remote version, the one that's plugged into your aircraft's telemetry port. You can do both on USB at separate points, and that's a good fail-safe if you need to do that. Mission Planner setup. This slide's just a couple of options that I like to set. One thing you should be looking at is making sure your units over here match what you've designed in. If you tell your aircraft you want it to fly at 100, but you have these units set to meters instead of feet, don't be surprised when it's 300 feet off the ground. Kind of the same thing for miles per hour or meters per second. Telemetry rates, the higher the number, the more fine your data will be. But some of that, they get sent back. You can reach bandwidth limits if you're not careful. Log path, that's just where you're saving all of your logs. You don't necessarily need to change that, just know where it sits. And then I highly recommend this advanced layout. I will show you, actually no I won't, because I don't have any to plug in. Anyhow, advanced layout gives you access to the more advanced parameters within the PICSOC. So another use for the software, you can run a simulation. You see the box at the bottom that says it's cheaper than crashing cheaper to crash a simulated plane than a real one. Very true. So it's a nice thing to get done. You can start now. You can use the basis plane in Mission Planner to set up a simulation, play around with it, see what the commands do, and everything like that. Once you get your aircraft integrated, maybe have your gains figured out more, you can plug it in, and maybe see what your aircraft really will do down to an okay level. It's not, as we say here, the fidelity is fairly low, but it's better than guessing. So that's a good thing to go at. Testing out new mission profiles and teaching other team members to fly be a nice goal for the teams. So in the simulation, to set it up, you click on simulation, select model here on the bottom, and then click plane. It'll download the software and the loop items. That's what SITL here is. It initializes a simulated plane. It'll say it connects via TCP if you're up in the right-hand corner of Mission Planner. And you can interact with it just as if it was a real plane. Load waypoints, you arm it. You can say fly a mission, and it'll go fly how it thinks that it would fly. Obviously, if you're just using the built-in plane, The values may not be perfectly, or may not even be similar to your real plane. So keep that in mind, that if you don't have those set up, it won't necessarily fly like your real aircraft. And you can change parameters on the fly. So that's a nice one to do. And just on the top right, you can just disconnect here to stop the simulation. We're on waypoint definition. Waypoints are inherently a three-dimensional item. Most people think of latitude, longitude, but there is also an altitude included. If you set an altitude of 0 for a waypoint, don't be surprised when the aircraft heads towards the ground. There's also a built-in latitude-longitude tolerance here, and it's a radius, right, not a diameter. So if you have a really big radius, as soon as it crosses that radius that is your tolerance, it'll start heading to the next waypoint. So in this example here, it crosses the radius for waypoint 1, and immediately starts heading towards waypoint 2. It crosses the radius for waypoint 2 and immediately starts heading for waypoint 3, and so on and so forth. So you very well may want to pare down those tolerances, the waypoint radius, to get those to an acceptable level. Obviously 1 foot may be too much, right? You fly right past it, and then it'll try to correct it and get back to it. And that's not necessarily a good thing either. And with altitude definition, there's 3 ways to define it. Absolute here is mean sea level, terrain is above ground level, and then relative is relative to your home point. Here in Indiana, relative and terrain are almost identical. Just use whichever is more correct for your mission. So there we have, on the top, we have a large radius waypoint for all of those. On the second picture here, we have a much smaller radius waypoint, so you can see the action of the plane as you have a smaller radius waypoint. Testing the software, the same thing. You need to know what you're getting into. Make sure you can do it before you need to go do it for real in front of the Boeing folks, right? So you set up your PIXLOC to be able to talk to your ground control station, test out your different modes. You can change modes with the ground station or your RC transmitter. Understand what the software is doing. Don't make an assumption. Don't guess. You should have this all down to a science by the time it gets to the fly off. I absolutely know what the fail-safes are and what to expect. When they will trigger, why they will trigger, what to do if they do trigger, all along those lines. And always be ready to take control back from the autopilot unless you've flown your mission tens of times and you know absolutely what it's going to do without any question. So integration, as Carl said the other day, may take as long as building the rest of your aircraft, including servo wires, putting servos in, hinges. It just takes a long time, especially if you've never done it before. I can't cover each individual aircraft, obviously. Everybody's is different. The missions are different. And you also need to tie back the integration and your aircraft performance back to your KPIs. You need to figure out what really needs to happen in this aircraft. It'll take you longer than you think, and usually there's a lot of tape used. So please don't do that. I will really encourage you to model absolutely every component you can: servo wires, servos, servo connectors, the screws that go into the servos, just everything you can if you've got time. A big one in integration, making sure you can access the PIXLOC. If you are putting components into individually, make sure you can then access them after you have put them in. Make sure you can plug your servos in. Make sure your ESC can reach your motor. Make sure your pedostatic pneumatic tubes are long enough. Just everything along those lines. When you get those all plugged in individually, make sure you can plug them into your PIXLOC. It is incredibly difficult if you've got a limited space to try to get fingers in a tiny little area to try to plug things in. So try everything you can to not have to wedge fingers in tiny little places. So leave bigger access holes than you think you need. Have it way out in the open. Just do what you can there. So also, this kind of goes back to the Iron Bird, the mock-up example. Make sure everything works before you plug it into your Pixhawk. Um, it's very common to think that the Pixhawk has an issue, but there's really a wire wrong down the road. Use a servo tester to troubleshoot individual servos. Make sure your prop's spinning in the right direction before you get everything sealed up. Sometimes you can change that in ESC programming, other times not. So once you have everything plugged in, you should have your telemetry radio set up and everything. And make sure you're very careful with the tiny connectors. They're really easy to break. The Pixhawk 2 is significantly better on all of that, but Pixhawk 1 and Pixhawk Mini, be especially careful. It's very easy to break things. Unless you're very prepared, you may not have a spare on the flight day. And go through your startup process. Once again, you should have a very good idea of how you're getting everything put together. You should have a flow chart or a checklist put together. You shouldn't have any questions the day of the flight. So then go fly. A very important thing before you go fly, make sure, even before this first note here, make sure that your gains are set such they are turning the aircraft correctly. For instance, if you have it on stabilized mode on the ground, no prop on, please. If you bank it left, it should try to bank itself back right. So that means the left aileron should go down, the right aileron should go up. Similarly, in the yaw, if you yaw it left manually, it should try to yaw itself back to the right. If you pitch up, it should try to pitch itself down. That is a very key thing. If you have that set incorrectly and it's ever on any kind of a stabilized or an auto mode, it will end up in the ground very quickly. So the first time you go fly it manually and then check the stabilize to make sure that it works. Make sure that it's you don't have any gain set too high. You don't have any oscillations going on. Once again, be prepared to take control away from your system. So arm it. There's a kind of a subtle thing between safing the system and arming the system. I don't think I covered it in depth. I mentioned it on a couple of slides. Safe essentially means that you're about ready to fly. Armed means you are ready to go fly, and the prop will spin, and the system there's no lockouts. So launch it, climb to safe altitude, engage your stabilizer, fly-by-wire mode. Make sure that it flies steadily. That's the big thing, right? Always be prepared to take control away from it. And you can check out this auto-tune. Really kind of a nice way to get the gain set, and you can go through and maybe tune those individually later. But it's a nice starting point. From what I've heard, it does, and I don't know what I've used, it turns out pretty well. Also, if you've got an aircraft that happens to be similar to some of these other aircraft that are in community submitted values, you can take a look at that for gains. So flight modes, there are a dozen maybe in Mission Planner that you can choose from. Auto does your mission plan for you, right? You can set up an automated takeoff, follow waypoints, loiter, drop payloads, anything like that. You can even automate landing. If you're going to automate landing, I would say be careful with GPS altitude. Barometric may be better, but you may need actually to even add a LiDAR to get more precise on it. You can hand fly with stabilized fly-by-wire cruise. And then these ad hoc ones where you can essentially flip a switch and it will set up an orbit above the point which you flip the switch. So there are built-in safeties to Mission Planner in the firmware. You can set up an envelope protection as a flight envelope protection. Prevent stalls, overspeed, so that's more or less preventing you from pitching the nose up, down, or rolling too far, as well as making sure that you're not diving straight at the ground with full throttle. Kind of a free insurance, highly recommended. You can trust that, but make sure it's actually working. Geofencing is kind of an artificial fence, as it says. Keep your plane in a specific area, in the flight box we're at, in Alabama maybe, or out of a specific area. I don't know what our flight will be like in Alabama, but if we have any areas that we would not like flying, we may like you to set up a geofence to keep you out of a specific area. And then terrain following, groups may or may not set that up. More or less, if you set it, there's a couple of the modes where it will essentially maintain the same altitude even in varying terrain. So tying this all together, when you're done with your flight, you can collect a ton of data. I recommend downloading the data flash logs as well as the telemetry logs from your Pixhawk, and you can go and post-process this to your heart's content. So you can get altitude, GPS locations, flight time, battery consumed, and I mean raw accelerometer values, channel values from your RC controller. There is limitless amounts, and if you've got the GPS plugged in and working, you should get a very accurate timestamp on each of those as well. You can check to see if you want to change controller gains. Maybe you don't like the climb out angle that it happened at, landing speeds, cruise speeds, all of that. You could do a pretty sophisticated flight testing program with all of this if you felt the need. So after you've got all that data, figure out what went right and anything that went poorly that you want to change for the next time. Another good thing to debrief is a 3D flight path, and the steps are here. I won't walk you through each of these individually. Suffice it to say, it used to be a lot easier when Google Earth was a thing that you could download and use. Now you have to go through this whole rigmarole of downloading a file and then re-uploading it in Google, but the results are pretty nice. You get a kind of a pretty picture here. This is the field we usually fly at, a 200-foot runway. And this was all flown manually, but you get kind of a cool picture of all of the different, pretty much everywhere you flew. So it's a good final report item, if nothing else. So once you have this, put all your plane together, you can go do your extensive flight test program, all under automated methods, and then you can go deliver your vaccines, watch wildfires, whatever else you want. A couple of common issues for integration. You say you can't connect to the mission planner over USB, check your COM ports. That's usually a pretty common issue. Over radio, make sure you have the correct net ID on both of them. Servos won't work. A couple of things you could do here. Check your servo wires, most common. For orientation, the top one here, see if you're actually getting power. There was a question earlier today about powering the servos, and that power needs to come through the connection where the servos connect to the Pixhawk. The power has to come through either a standalone BEC, or if your motor or your speed controller has a built-in BEC, that can come in through channel 3 on the outputs, on the servo outputs. The power module that plugs in between your battery and your speed controller and then to the Pixhawk is only powering the brains of the Pixhawk. It's not powering the servos. And then also checking to see if channels are enabled when the aircraft is either unsafe or not armed. And kind of related to that, if you say it won't arm, check in the parameter list, this box down here. I think by default all selection is checked, but if you haven't plugged in an airspeed sensor or a barometer, you're not going to have status for that, and it won't let you arm the aircraft. So homework for the teams, please set your telemetry radios, that net ID, to the following channels. It's just 10, 20, 30, 40, 50. Nothing hard, it should only take a couple of minutes, but it should eliminate some of the problems we had last year with fly off. I'd also like to hear what the teams are doing video frequency wise, as far as live feedback, making sure we don't have any interference the day of the flights either. That should be another, actually even easier remedied one than the telemetry radio channels. A little bit of related reading here. The APM plane website is linked. I'll show you that in a second here. This book is just 2nd edition, 3rd edition. The 3rd edition has a chapter on UAVs, SUAS. I've got this one. If anybody would like any references from it or anything, I can help you out with that. And then please shoot me an email with any questions. I would be glad to help anybody out with that. So Mission Planner. You have the RG Plane website. It's just rgpilot.org/plane. It's linked in the PowerPoint, which is on SharePoint. It's got an introduction, first time steps. It has tutorials for almost everything that's built in the Mission Planner here. It can get very in-depth. You can get easy answers to some things. Transmitter-based tuning, if you want to try to tune stuff on the fly, you can do some very interesting things with everything that's happening for all this. So, what's flight features? Actually, might be some excellent spots. Stall prevention would be a great thing for teams to include. Geofencing, as I mentioned, very useful to have. Let's see what's in advanced configuration. Some other communications, CAN bus, that parameter list that I had mentioned, and how to use all of the RC outputs if you need to change anything particularly. And that's about it from this website. Please just take a look if you've got. Here's a thing on simulation. If you've got, if you have questions on this, there's a ton to dig through here. If you don't find an answer, please let me know, and I'll see if I can help you out with finding any of that. Mission Planner here, and this is probably a slightly older version, maybe just by a couple of builds than what the current one on the website is. Mainly here, this is the flight data tab. You just have flight data, flight plan, initial setup, configuration tuning, simulation, and terminal if you want to write some custom codes here. Flight data, if you have it connected, this is your artificial horizon. It'll show the aircraft's orientation, speed, altitude, and rates for both of those. Up on the top here, you have a directional, your compass, and bank angles up here. It also gives you status, EKF, extended Kalman filter, GPS, currently nothing plugged in, so no GPS. Then you have so just some raw values here. This Actions tab is where you can do a lot of things while you're in the air. So if you are flying manually and you say, oh, I kind of want to look at that, you can click Loiter Unlimited and say Do Action. It'll start loitering there, and it'll just keep circling until you tell it to do something else. You can set modes in this tab, in this drop down. RTL is return to launch. You can retract and extend mounts, radio mounts usually. You can set up or use your joystick. Arm and disarm the plane is a very important one that's kind of sometimes hard to find. It's in here as well. Just a whole bunch of stuff you can do in here. Another good one to check is telemetry logs. You can go back and essentially watch a previous flight. Data flash logs is where you can plug into your Pixlock after a flight, download these data files, and then really go hog wild with the post-processing. So have fun with that. In the flight plan tab, that's where you can set up a, any kind of a flight that you want. So if we're going to say, let's see if we can zoom in a little bit here. We want a waypoint there, and here, and here, and here. Okay, cool, that looks good. Down at the bottom is where you have what these commands are. Why don't we add, we'll insert a waypoint here, and we can drag it around. Oops, drag the wrong one. We'll leave waypoint 2 where it is, if I can grab it. And we'll delete waypoint 6 that I just added. There we go. And we'll call waypoint 1. We want that to be a takeoff instead. So the altitude there is going to be 0. So then it tells you, oh, and this is our home must be set kind of funny. Anyhow, it'll tell you the latitude, longitude, as well as what the angle is to the next waypoint. So this one is 33 degrees, which is quite a bit. Not usually a very useful one. So about the radius of these waypoints here, you can change that in here. My units are set to feet, so let's say I want a 25-foot radius. Do that, and they change pretty small. Maybe it's too small, maybe it's not. Leave that for you to figure out. You can also set default altitudes here. Maybe I want to loiter above this point for 8 turns. Except we want this to be ordered up. There we go, between 3 and 4. So after waypoint 3, it'll head towards waypoint 4, loiter for its 8 turns, and then continue on a flight path. So that's more or less how you do this. If you've got a flight path made that you like, you can save it locally. Saving is to your local machine. If you do write waypoints, that is where it sends it to the aircraft that's currently connected, or perhaps even the simulated aircraft if you have that connected. So that's how you use that for the most part. You can spend hours playing around with it, figuring out what you really want to do. Configuration tuning, since I don't have anything plugged in aircraft-wise or Pixhawk-wise, usually you have options here for the whole things in the aircraft, but otherwise you're just left with the screenshot I had shown earlier with all of these options selected. Initial setup, you can go through the first setup here, and you can do the SIK radio without having any of that plugged in. But that's the long and short of Mission Planner. There's hours and hours and hours worth of items that you can go through here. I'd really encourage you just to take a look, do what you can ahead of the fly off in the next couple of months to get associated with this and make sure that you can use it when it comes down to it. Well, once again, if anybody has any questions, please let me know. Other than that, I hope you found this informative, and have a nice